Now we're going to start the topic of systems of equations, and in this section we're going to talk about systems of linear equations in two variables. So an example of this is given here, what a system of linear equation in two variables looks like. Basically we have two equations and two variables. Here we're going to look at x plus 2y equals 2 and x minus 2y equals 6. So when we solve a system of equations like this, we're trying to solve for both unknowns, both x and y here. And so first off, let's see what would a solution actually look like for a system. So for instance, we might have 4 comma negative 1 and negative 4 comma 3. And so these are both numbers, both for x and y. So the first one would be x, the second number would stand for y. And what we're going to start off doing is figuring out if either one of these represents solutions to the system of equations. And the way we're going to tell that is we're going to substitute the numbers in for x and y. So we're going to start off with 4 comma negative 1. And we'll substitute x equals 4 and y equals negative 1. So that would look like 4 plus 2 times negative 1. And we're checking in that equation if it equals to 2. And then 4 minus 2 times negative 1, we're checking if that equals to 6. On the first equation, that would be 4 minus 2. That does indeed equal to 2, so that one checks out. Down here we'd have 4 plus 2, and that equals to 6, so that one checks out. So since this value for x and y checks out in both equations, we can say that 4 negative 1 is a solution. Now it is possible in some of these cases to get more than one solution. So let's see if negative 4 comma 3 also is a solution. So we're going to substitute x equals negative 4 and y equals 3. So in the first equation that would look like negative 4 plus 2 times 3. We're checking, does that equal to 2? And the second equation, it would be negative 4 minus 2 times 3. And we're checking to see, is that equal to 6? So in the first equation, we're going to get negative 4 plus 6, and that indeed is equal to 2. On the second equation, we're going to have negative 4 minus 6. That one doesn't work, it's not equal to 6. So we see that checks out in one equation, but it doesn't check out in the other. So this one is not a solution to the system. So what we can tell then is if it's a solution, it has to work in both equations at the same time. Now one way of starting to visualize and see where the solutions exist is to actually graph the system of linear equations. And so here we have the two equations, and all we would have to do is graph each of these as straight lines. So if we graph the lines, one of these lines is going to pass through 2 as its x-intercept and pass through 1 as its y-intercept. If we were to go to find the x and the y-intercepts for one of those lines, this is what we would find out. X plus 2y equals 2 would pass through the y-intercept of 1 and x-intercept of 2. If we find the x and y-intercepts for the second equation, it would have a y-intercept of negative 3 and an x-intercept of 6. So we'd see the line would pass through like so. And where these two lines intersect for both of these equations, that'll be the solution to the system. So here we see them intersecting at the point 4 comma negative 1 roughly, as accurate as my graph can be here. And so we can always see a solution to a system if the two lines for the two equations intersect at a point. So we saw how if the two equations have lines which intersect at a single point, then we have one solution where they intersect. But that's not always the case with two straight lines in a system of linear equations. It could turn out that the lines fall on top of each other. And if they fall on top of each other, then they intersect everywhere along the line. And so in those cases, there are infinitely many solutions. And we call it a dependent system of equations. The third situation is if the two lines are parallel, and thus they would never intersect each other. And so in those cases, there's no solution. And the name for that is an inconsistent system of equations. So those are our three situations. They might intersect, we get one solution. They may fall on top of each other, in which case we get infinitely many solutions. Or they might be parallel, never intersect, and there will be no solution to the system. So we're going to look at some different ways of going about solving these algebraically rather than graphically. And the first way we're going to talk about is solving by substitution. I have the steps listed out in the handout for this section. The first step is to solve for one of the variables in the system of equations. So if it's x and y, we would solve one of the equations for x or solve one of the equations for y. And then we take what we find from the first step and substitute it in to the other equation. This will give us an equation of just one variable, which we can then solve for that one variable, and then substitute that solution that we get into either one of the equations to solve for the other remaining variable. And then this last step we'll do occasionally. We will check to see if the proposed solution works in both equations. Okay, so our first situation here, we have 5x minus 4y equals 9, and x minus 2y equals negative 3. And we're going to solve this by substitution. Now what we're going to do is we're going to choose either one of these equations, equation 1 or equation 2, we can call them, and solve one of those equations for either x or y. We usually try to find the one that looks the most convenient. So here what I'm going to do is I'm going to solve equation 2 for x. And to solve equation 2 for x is just a one-step process. I'll add over the 2y and make this into x is equal to 2y minus 3. And then what I'll do is I'll take the thing that I just solved and substitute that into the other equation. So we're going to substitute x equals 2y minus 3 into equation 1. So if we do that, we're going to have 5 times 2y minus 3 in the place of x minus 4y equals 9. And then what I'll do is I'll go ahead and distribute the 5. We'll get 10y minus 15 minus 4y equals 9. And then at this step, what we're really trying to do is just solve for y. It's just a now equation with one variable. We'll get 6y minus 15 equals 9. We'll add over the 15 to both sides. 6y equals 24. And then what we'll do is we'll divide the 6 to both sides, and what we'll get is y is equal to 4. So that's one solution of our system of equations. Now what we'll do is we'll substitute this y equals 4 into either equation 1 or equation 2. So we can choose either one to use. But here I'm going to go ahead and substitute y equals 4 into equation 2. So again, equation 2 is x minus 2y equals negative 3. So it would be x minus 2 times 4 equals negative 3. X minus 8 equals negative 3. And after adding the 8 over, we'll find x is equal to 5. Okay, so those should be the numbers for our solution. But just to be safe, let's go ahead and check. So to check, we're going to plug in the numbers for both x and y in both equations up above. We're going to plug it into equation 1, and we're going to plug them into equation 2. Plugging it into equation 1, we'd have 5 times 5 minus 4 times 4, and we're checking to see, is that equal to 9? So if we do that, it would look something like 25 minus 16, and we'll see, is that equal to 9? Indeed it is, so that checks out. And the other equation, we'd have 5 minus 2 times 4, and we're checking, is that equal to negative 3? So looking at the numbers here, that'd be 5 minus 8, and that indeed is equal to negative 3. So it all checks out here. We'll write it as x comma y, 5 comma 4. Okay, let's try another one by substitution. Here we have y equals 3x minus 2 and 15x minus 5y equals 10. Now notice how the equation 1, the first equation, is already solved for y. So if it's already solved for y, what we can go ahead and do is substitute y equals 3x minus 2 into equation 2. Okay, and if y'all like to try this as practice, go ahead and pause the video, and in just a second I'll work through. You can go ahead and practice it, and then when I come back I'll go ahead and work through how this one would go from here. So substituting this in, we'd have 15x minus 5 times 3x minus 2 is equal to 10. Okay, after we distribute the negative 5, we'd have 15x minus 15x plus 10 is equal to 10. And then something interesting will happen. The 15s will go ahead and go away, positive and negative, and we'll be just left with 10 equals 10. So now our variable has disappeared. There's nothing left to really solve. But what we're left with here is 10 equals 10, which is technically true. So we're not looking at something ultimately a false. But when our variable goes away and we're left with something that still is true, the two numbers are identical, then what that tells us is we have infinitely many solutions. So this is the situation. If you were to graph the two lines, you'd find that they're parallel to each other and they never intersect. So this is what happens in the algebra, though, when we run into a infinitely many solutions system of equations.